For over 400 years, astronomers studied the Milky Way, unable to see through vast cosmic dust clouds. Millions of stars, entire spiral arms, stellar nurseries, and the galaxy's true warped shape remained hidden. Revolutionary infrared technology has now revealed these features. Astronomers studying our galaxy faced a persistent challenge. We reside within the Milky Way's disk, surrounded by stars and cosmic debris that severely block our view. In 1609, Galileo resolved the Milky Way's cloudy band into individual stars. Unaware he was seeing the edge-on view of a massive spiral galaxy containing 400 billion stars. For 3 centuries, astronomers reconstructed galactic structure using visible light, mapping star brightness, stellar densities, and motions. However, visible light is blocked by cosmic dust, microscopic particles of silicon, carbon, and iron. These dust grains, though tiny, form vast clouds hundreds of light years thick, capable of hiding entire star clusters. By the 1950s, astronomers had mapped less than 10% of the Milky Way. Beyond a few thousand light years from Earth, the view was obscured. The galaxy's spiral arms, central black hole, full stellar population, and star-forming regions were hidden. While distant galaxies suggested a spiral shape for our own, detailed understanding was lacking. A method to see through the dust was needed. Cosmic dust consists of microscopic particles, remnants of ancient stars from supernova explosions, seeding the galaxy with heavier elements. These particles clump into vast clouds. The galaxy contains enough cosmic dust to build 10 million Earth-sized planets. The problem is not just the quantity of dust, but its distribution. Cosmic dust congregates in the galaxy's disk, where most stars, including our Sun, reside. From this vantage point, looking toward the galactic center or along spiral arms means staring through thousands of light years of accumulated particles. Only by looking perpendicular to the galactic plane can we see clearly into intergalactic space, explaining why distant galaxies are observable, while our own remains largely obscured. Dust affects different light wavelengths, scattering blue light more easily than red. By the mid-20th century, astronomers understood the limitation. They could see only about 5,000 light-years in most directions, less than 5% of the 100,000 light-year spanning Milky Way. Star clusters, spiral arms, and star-forming regions were hidden. However, cosmic dust does not block infrared light. Infrared radiation, with wavelengths roughly 10 times longer than visible light, interacts differently with cosmic dust. Its longer wavelength allows it to pass through dust particles that block visible light, effectively seeing through what appears to be an impenetrable wall. The breakthrough came in the 1960s, with the launch of infrared telescopes above Earth's atmosphere, which absorbs most infrared radiation. From space, infrared detectors peered through the galaxy's dust, revealing stars invisible to optical telescopes and making transparent dust clouds that had obscured star-forming regions. Astronomers could now see the Milky Way's central regions, hidden behind 26,000 light-years of dust. Spiral arms and star clusters, previously invisible in optical light, became visible. Infrared light also revealed the dust itself, which absorbs visible and ultraviolet light and re-radiates it as infrared. This allowed astronomers to map dust clouds, tracing gas and dust flow, star formation, and dispersal by stellar explosions. Early infrared surveys were limited, providing only small, low-resolution maps. A systematic, comprehensive infrared survey of the entire galaxy was needed. High in Chile's Atacama Desert, VISTA, the Visible and Infrared Survey Telescope for Astronomy, is the largest infrared survey telescope ever built, with a 4-meter mirror. Its systematic mapping approach allows it to map enormous swaths of sky with high precision, unlike telescopes that take individual images. VISTA's camera contains 67 infrared detectors, cooled to 300 degrees F, 184 degrees C, sensitive enough to capture individual photons. VISTA maps specific galactic regions in multiple infrared wavelengths. Some reveal hot young stars, others cool old giants, and others trace cosmic dust. The VISTA variables in the Via Lactea (VVV) survey has spent over a decade photographing dust-obscured galactic regions, generating images with roughly 67 million measurements of starlight. The survey accumulated over 500 terabytes of infrared imagery, creating the most detailed infrared atlas of the Milky Way. This systematic approach produced the first comprehensive three-dimensional map of our galaxy's structure, from its innermost regions to its outermost spiral arms, revealing its true stellar population. Within weeks, VISTA discovered 96 star clusters, each containing thousands or tens of thousands of stars. Previously invisible to optical telescopes, these clusters are stellar families born from the same cosmic cloud. This rapid discovery revealed numerous unknown clusters. Many clusters were concentrated near the galactic center, behind thick dust clouds, or embedded in spiral arms. Some were so obscured they absorbed over 99% of their visible light. For example, VISTA revealed a cluster behind Sagittarius with over 10,000 stars, invisible to optical telescopes despite being only 15,000 light-years away. Another ancient cluster contained stars over 10 billion years old, providing clues about the Milky Way's early history. VISTA pushed deeper into infrared regions, revealing millions of individual stars. Our galaxy contains 3 billion more stars than previously observed, many of them massive, bright giants, hundreds of times more intense than our sun, hidden behind dust clouds. This discovery unfolded as VISTA systematically mapped regions, each revealing stars where optical telescopes saw darkness. Many were red giants in their final life stages, rendered invisible by dust. Others were young, hot stars, recently born from collapsing gas clouds. Each newly visible star provided data for understanding the galaxy's structure, composition, and history. Astronomers could measure stellar distribution, trace the true shape and extent of spiral arms, and map unknown stellar populations. Discoveries from the galaxy's central regions revealed vast star populations surrounding the central black hole, creating the first three-dimensional picture of the galactic core. Deep within the galaxy's most obscured regions, VISTA unveiled stellar nurseries, vast regions where gravity forms new stars from gas and dust over millions of years, within cocoons impenetrable to visible light. While radio emissions and gravitational effects were detected previously, VISTA directly revealed the stellar birth process in infrared light. Astronomers could peer inside, watching gravity sculpt raw cosmic material into protostars, the earliest phase of stellar development. They could trace how stellar winds and radiation from new stars carved out cavities. VISTA revealed star formation as a dynamic, ongoing process. A massive star-forming complex behind Cygnus, appearing as a dark patch to optical telescopes, was revealed by VISTA to contain over 2,000 newly forming stars, producing the equivalent mass of our Sun in new stars every few thousand years. Another hidden nursery near the galactic center revealed dozens of massive protostars. These discoveries showed star formation continues even in crowded and chaotic regions. While VISTA revealed hidden stars, the Gaia spacecraft measured their positions with high accuracy. Launched in 2013, Gaia's mission is to measure the position, distance, and motion of every visible star. Gaia detects stellar parallax as Earth orbits the Sun, measuring angular shifts in milliseconds for millions of stars simultaneously. By repeating measurements over several years, Gaia reveals stellar distances accurately. Gaia also tracks stellar motion, detecting proper motion, stars' movement across the sky perpendicular to our line of sight, by comparing positions over months or years. This combination of distances and motions allows astronomers to reconstruct the three-dimensional architecture of our galactic neighborhood, revealing stars as objects moving through 3D space on their orbital paths. Gaia's first major data release in 2016 contained precise measurements for over 1 billion stars. The second in 2018 added stellar velocities, chemical compositions, and surface temperatures. These releases advanced our understanding of galactic structure, especially when combined with VISTA's infrared discoveries. Combining VISTA's infrared discoveries with Gaia's precision measurements created the first three-dimensional map of our galactic neighborhood. Stars exist in 3D space, moving in complex orbits. Creating a 3D map required determining distance, as two stars appearing close could be vastly distant. Gaia measured parallax for millions of nearby stars. Beyond a few thousand light-years, VISTA became crucial, revealing millions of dust-obscured stars invisible to Gaia. Many of these hidden stars belong to stellar populations with known properties. By measuring their infrared brightness and comparing it to their expected intrinsic luminosity, astronomers calculated their distances using photometric parallax. Combined with Gaia's data, this created a three-dimensional stellar census throughout the galaxy. Astronomers can now plot stars in 3D space, tracing orbits, mapping populations, and reconstructing the galaxy's structure. The resulting maps are 3D models. Analysis of these 3D maps revealed a shocking discovery. The Milky Way is not a neat, flat disk. Our galaxy is twisted into a complex, warped shape. The galactic disk bends and curves, particularly toward the outer edges, where it curves thousands of light years upward and downward from the galactic plane. This effect was detected by precisely mapping millions of stars across vast distances. The discovery explains mysteries like hydrogen gas clouds observed above and below the galactic plane that didn't match theoretical models, as these clouds follow the galaxy's warped structure. The warping suggests gravitational influence from the large and small Magellanic Clouds, whose orbits have gradually twisted the galaxy's outer regions. The warping is dynamic. Simulations show the galaxy's shape changes as it rotates, with regions curving upward and downward in a wave-like pattern that travels around the galaxy every few hundred million years. This discovery revised galactic dynamics. The Milky Way is part of a gravitational ecosystem where nearby galaxies, dark matter halos, and cosmic gas flows shape its structure. Beyond the warped shape, closer examination of the disk's spiral pattern revealed a more complex galactic architecture. Our galaxy was hiding entire spiral arms, invisible to optical telescopes. For over a century, astronomers mapped 4 major spiral arms based on bright young stars and glowing gas clouds, but cosmic dust limited these observations. When VISTA's infrared data combined with Gaia's 3D measurements, the galaxy's true spiral pattern emerged, revealing a more intricate structure. Hidden spiral arms appeared from behind dust clouds, some extending farther from the galactic center, others between major arms, creating a complex network of stellar streams and bridges. One discovery was a previously unknown spiral arm extending from the far side of the galactic center, hidden behind 26,000 light-years of dust and gas. This arm contains millions of stars and stretches for tens of thousands of light-years, suggesting a more symmetrical spiral pattern. Feather structures, smaller spiral segments branching off major arms, were also found, containing their own star populations and star-forming regions. The galaxy's spiral arms are an interconnected network, channeling gas, dust, and stars. The new maps showed that spiral arms are dynamic, forming, evolving, and dissipating over hundreds of millions of years as density waves propagate. Stars move in and out of spiral arms. Infrared observations revealed some spiral arms contain older stars never before detected, preserving evidence of ancient spiral structure and allowing reconstruction of its evolution. The 3D maps also revealed ancient cosmic violence. Gaia discovered evidence of cosmic crashes. Analyzing 3D motions of millions of stars, astronomers found large groups of stars moving in coordinated ways with chemical compositions that didn't match their galactic neighborhoods. These stellar streams indicated ancient catastrophes. The evidence indicated our galaxy has been involved in multiple collisions with smaller galaxies over the past 10 billion years. Each collision left distinctive stellar population fingerprints, creating groups of stars with shared origins, ages, and unusual orbital patterns. A massive collision, 8 to 10 billion years ago, involved a galaxy roughly a quarter the size of the Milky Way, named Gaia Enceladus. This collision scattered stars and reshaped the early Milky Way. Stars from Gaia Enceladus have different chemical compositions and distinctive orbital patterns, highly elliptical paths compared to native Milky Way stars. Gaia Enceladus wasn't the only collision. Data revealed at least 6 smaller collisions, each involving millions or billions of stars. These discoveries changed our understanding of galaxy growth. Galaxies like the Milky Way grow primarily through cannibalism, devouring smaller neighbors and incorporating their stellar populations. This evidence also explains puzzling stellar populations. Gaia discovered stellar streams surrounding our galaxy, rivers of stars torn from smaller galaxies. These streams stretch for hundreds of thousands of light years, wrapping around our galaxy in long, thin ribbons of stars, sharing common origins, ages, and chemical compositions. They are remnants of galactic cannibalism, preserving the shapes of destroyed galaxies. When a smaller galaxy ventures too close, the Milky Way's gravitational field stretches it via tidal disruption, pulling stars away to create debris streams. The Sagittarius Stream is an example, a ribbon of stars wrapping around our galaxy multiple times, containing remains of the Sagittarius dwarf galaxy, which the Milky Way has been devouring for over 1 billion years. Gaia revealed over 60 distinct stellar streams, each representing a smaller galaxy's destruction. These streams, fresh or ancient, tell unique stories of cosmic destruction, with stars sharing chemical compositions and ages, allowing reconstruction of orbital histories. Stellar streams actively reshape our galaxy, gravitationally influencing its structure, contributing to disk warping and heating, and sometimes triggering accelerated star formation. This galactic violence is how galaxies grow and evolve. At the heart of our galaxy is Sagittarius A, SGRA Inch, the supermassive black hole anchoring the galactic center. It weighs 4 million suns, crushed into a region smaller than our solar system. For decades, SGRA was hidden behind dust and gas, detected only by radio emissions and nearby stellar motions. VISTA's infrared observations revealed SGRA's sphere of influence, where its extreme gravity dominates behavior within 10,000 light-years. VISTA's infrared observations revealed thousands of stars orbiting SGRA in highly elongated paths, some approaching within a few billion miles of the black hole's event horizon, at speeds over 12,000 miles per second, 19,300 km/s, experiencing time dilation. The black hole's influence organizes the entire central region of our galaxy. Star formation patterns, gas flows, and cosmic dust distribution show SGRA's gravitational pull. SGRA actively feeds on nearby material, creating an accretion disk of superheated gas glowing in infrared light. It can outshine billions of stars, blasting high-energy particle jets thousands of light years from the galactic center, sculpting vast hot gas bubbles. Infrared observations also revealed SGRAC's gravitational influence, sculpting stellar populations for billions of years, with ancient stars near the galactic center showing chemical signatures explained by repeated close encounters and tidal forces. The central black hole is one component of a larger architectural framework shaping our galaxy. An invisible scaffolding made of the universe's most elusive substance lies throughout our galactic neighborhood. Our galaxy is embedded within a massive halo of dark matter that outweighs all visible stars by 10 to 1. Dark matter doesn't emit, absorb, or reflect light, interacting with normal matter only through gravity, making it invisible. This substance provides the gravitational scaffolding that holds our galaxy together and determines its shape and structure. Without it, the Milky Way would have torn itself apart billions of years ago. Dark matter creates an invisible framework supporting the galaxy's visible components and guiding their evolution, much like a skeleton determines a body's shape. Evidence for dark matter comes from the motion of stars and gas. When astronomers measure star orbits around the galactic center, they find stars in the outer regions move too fast. Distant stars should orbit slower. Throughout the Milky Way's disk, stars orbit at roughly the same speed, about 500,000 miles per hour, 800,000 km/h, regardless of distance. This is explained only by much more unseen mass extending far beyond the visible stellar disk. Gaia's precision measurements of stellar motions allowed astronomers to map this dark matter halo in detail. Data reveals our galaxy sits at the center of a roughly spherical dark matter distribution, extending at least 300,000 light-years from the galactic center, 3 times larger than the visible galaxy. This dark matter halo contains over 1 trillion solar masses of material, creating the gravitational environment, allowing spiral galaxies like ours to exist. Dark matter isn't uniformly distributed. Simulations based on Gaia's data suggest the halo contains substructure, clumps, streams, and smaller halos, left over from ancient collisions with dark matter-rich dwarf galaxies. These substructures might gravitationally influence nearby stars. The dark matter halo plays a crucial role in galactic evolution, storing gas that fuels star formation. Its gravitational field channels, gas flows, and sustains a stable gravitational environment for structures like spiral arms and stellar populations to evolve. Without it, our galaxy would be chaotic. Stars constantly migrate across the galaxy. Gaia's precision measurements revealed stellar migration as an important process shaping galactic evolution. Stars born near the galactic center can end up in outer regions, and vice versa. This shuffling takes billions of years. Migration is driven by the galaxy's spiral arms, which act like gravitational waves. When a star encounters a spiral arm, its gravitational influence changes its orbital energy. Over many encounters, these changes accumulate into shifts in orbital radius. VISTA's infrared observations revealed the consequences. Old, metal-rich stars, which formed near the galactic center, now exist throughout outer regions. Conversely, some areas near the galactic center contain young stellar populations that migrated inward. This discovery solved puzzles, explaining why stellar chemical compositions vary smoothly across the disk, despite different star formation histories. Migration mixes stars, carrying their chemical signatures to new neighborhoods. Our sun is a migrant star. Based on its chemical composition and age, it formed roughly 26,000 light-years from the galactic center, about 4,000 light-years closer than its current position. Over 4.5 billion years, gravitational interactions with spiral arms pushed our solar system outward to its present galactic habitable zone. This migration may have been important for life on Earth, as inner regions have higher rates of stellar explosions and radiation. Stellar migration is one way the galaxy preserves its past. The chemical compositions and ages of migrant stars contain a detailed record of galactic history. VISTA and Gaia's chemical analysis of millions of stars revealed that our galaxy preserves a fossil record of its evolution, stretching back over 13 billion years. Each star's atmospheric chemistry reflects its birth environment. The oldest stars contain almost pure hydrogen and helium, formed in the early universe before massive stars manufactured heavier elements. Younger stellar populations show progressively higher concentrations of heavier elements, carbon, oxygen, silicon, iron, from supernovas. Each stellar generation enriched the galactic environment. Sharp changes in elemental abundances mark specific episodes when major events disrupted stellar evolution, such as the Gaia-Enceladus collision 8 billion years ago, which left distinctive chemical signatures. VISTA's infrared observations were crucial for galactic archaeology, revealing cool, ancient red giant stars with primitive chemical compositions, often invisible to optical telescopes, allowing study of the galaxy's chemical evolution. The chemical record also reveals different evolution rates across the galaxy. Among these stellar populations, VISTA discovered groups of stars that didn't fit existing models of galactic evolution. VISTA discovered stellar misfits, groups of stars with chemical compositions, ages, and orbital patterns that contradict galaxy formation and evolution models. Young, metal-rich stars appeared in regions expected to contain only ancient populations, and ancient stars with unusual chemical signatures appeared where only recently formed stars should exist. One discovery was ancient stars within the galaxy's thin disk, where our sun resides. These stars are over 10 billion years old, yet orbit in the same flat plane as much younger stars. Standard models predict old stars should be scattered by gravitational interactions, making their confinement to the thin disk a paradox. Another surprise was young star clusters, in regions where star formation should have stopped billions of years ago, such as active stellar nurseries in the galaxy's outer halo. These newborn stars must have formed from gas preserved, despite surrounding hot, ionized material that should prevent star formation. Stars with chemical compositions that didn't match known stellar formation processes were also found. Some contained unusual ratios of heavy elements, suggesting exotic stellar explosions or nucleosynthesis. Others showed evidence of contamination from white dwarf or neutron stars, suggesting complex histories. A group of stars near the galactic center appeared to be moving backward through time. Their chemical compositions suggested recent formation, but their orbital motions and spatial distribution matched patterns of much older stellar populations. These stars challenge assumptions about how stellar ages, chemistry, and dynamics are related. These unexpected populations are rewriting our understanding of galactic evolution, suggesting it was more chaotic and complex than realized, with multiple episodes of star formation, chemical mixing, and structural reorganization happening simultaneously. Invisible magnetic highways guide the flow of cosmic materials across our galaxy, channeling gas and steering star birth. The Milky Way's magnetic field, though weak, shapes galactic structure, guiding ionized gas, cosmic rays, and star-forming material along field lines from the galactic center to its edges. Cosmic gas flows along magnetic field lines, creating structures mirroring the galaxy's magnetic architecture. These magnetic highways can funnel star-forming material across vast distances, triggering stellar birth in barren regions. VISTA's infrared observations revealed magnetic field influence in cosmic dust cloud structure. Tiny dust grains align with magnetic field lines. When infrared light passes through these aligned grains, it becomes polarized, tracing the magnetic field's direction and strength. Mapping this polarization created the first detailed charts of our galaxy's magnetic field. The maps revealed a magnetic field architecture more complex than imagined. It follows intricate spiral patterns, wrapping around the galaxy, intertwined with the spiral arms, suggesting co-evolution. The galaxy's magnetic field acts as a particle accelerator, boosting cosmic rays to high energies as they spiral along field lines, influencing star formation rates. The magnetic field also plays a role in stellar birth. Strong fields can hinder gravitational collapse, but also focus material, accelerating star formation. Observations suggest the magnetic field has been shaped by collisions, with smaller galaxies' magnetic fields interacting with our galaxy's field during tidal disruption. Magnetic fields aren't the only hidden structures in the galaxy. For over a century, fuzzy patches of light in our galactic neighborhood were cataloged as loose star collections or disrupted clusters. Gaia's precision distance measurements and VISTA's infrared revelations overturned this assumption. Many star clouds were actually intact dwarf galaxies, complete stellar systems containing millions of stars, their own dark matter halos, and independent evolutionary histories. Their low surface brightness and sparse stellar populations made them nearly invisible against the Milky Way's structures. The Canis Major dwarf galaxy, previously thought to be a disrupted star cluster, was discovered to be the closest galaxy to our own at only 25,000 light-years. This dwarf galaxy is actively being torn apart by the Milky Way's gravitational tides, creating stellar streams. The Sagittarius dwarf elliptical galaxy, hidden behind the galactic center's dust and gas, remained undiscovered until 1994 due to dust. VISTA's infrared vision revealed it as a substantial galaxy with over 1 billion stars. These satellite galaxy discoveries revealed our galactic neighborhood is far more crowded. The Milky Way exists within a complex ecosystem of smaller galaxies, each following its own orbital path. These hidden galaxies provide information about dark matter and galaxy formation, embedded within their own dark matter halos, creating gravitational fingerprints that help astronomers understand dark matter on small scales. The discovery of hidden satellite galaxies raised a question: where does our galaxy end and intergalactic space begin? Our galaxy doesn't have a sharp edge. It gradually fades into intergalactic space across distances that exceed previous estimates. For decades, textbooks stated our galaxy spans roughly 100,000 light-years, based on optical observations limited by dust and faintness. VISTA's infrared surveys and Gaia's precision measurements revealed the galaxy's edge is a gradual transition, extending much farther. The new observations revealed that our galaxy's stellar halo extends at least 500,000 light-years from the galactic center, 5 times larger than the traditional disk diameter. This halo contains billions of stars at low densities, missed by previous surveys. Many are ancient, preserved in the outer reaches. The galaxy's dark matter halo extends much farther, with simulations suggesting the Milky Way's gravitational influence reaches nearly 2 million light-years. Within this gravitational sphere of influence, the distinction between the Milky Way and its satellite galaxies blurs. The large and small Magellanic clouds, traditionally separate, may be embedded within our galaxy's extended dark matter halo. Other independent satellite galaxies might be gravitationally bound components of a single, vast galactic structure. This expanded definition of our galaxy's size has implications. Earth orbits a star within a vast gravitational ecosystem, extending across millions of light years, containing dozens of satellite galaxies, stellar streams, and reservoirs of dark matter and cosmic gas. This context is crucial for understanding our galaxy's relationship with its neighbors. Revealing the Milky Way is part of an intricate network of gravitational connections. The combined revelations from VISTA and Gaia have rewritten the story of how our galaxy formed and evolved. Traditional models described a peaceful process of slow mass accumulation and orderly star formation, portraying the Milky Way as a stable system. New observations revealed this narrative was incorrect. Our galaxy's history is a violent saga of cosmic cannibalism, collisions, and ongoing structural evolution. The Milky Way grew primarily by devouring smaller galaxies, incorporating their stars, gas, and dark matter. Galactic archaeology, using stellar ages and chemical compositions, revealed at least 3 major collision events reshaped our galaxy. The destruction of Gaia Enceladus, 8 billion years ago, significantly impacted it. Stellar streams from recently disrupted galaxies show that galactic cannibalism continues today, with the Sagittarius dwarf galaxy actively being disrupted by the Milky Way's gravity. This destruction will continue for billions of years. Archaeological evidence also revealed that star formation hasn't proceeded steadily. The galaxy experienced bursts triggered by collisions, followed by quieter periods. Galactic archaeology showed our galaxy's spiral structure is much younger than the galaxy itself, formed within the past few billion years through gravitational interactions. Previous spiral structures were destroyed and reformed multiple times. This rewritten galactic history has implications for planetary formation and life. Violent early epochs created hazardous environments. The galaxy's gradual transition to a more stable configuration may have been necessary for complex life. Our galaxy's dynamic history connects it to a vast cosmic web. Just 50 years ago, our cosmic address seemed straightforward. Earth orbits the Sun, one star in the Milky Way, an isolated spiral galaxy. This implied a stable cosmic environment. Today, our address is far more complex and dynamic. Earth orbits a migrant star that has traveled thousands of light years, carrying our solar system through changing galactic neighborhoods. Our Sun exists within a galaxy constantly consuming smaller neighbors, embedded in stellar streams from destroyed galaxies and permeated by magnetic fields. This dynamic cosmic context has implications for life on Earth. Our solar system's migration from inner regions to outer suburbs may have been crucial for complex life. The timing of major galactic collisions and resulting radiation bursts may have influenced mass extinctions and evolutionary bursts. Our expanded cosmic address reveals an evolving cosmic ecosystem that will create new stellar neighborhoods, planetary systems, and possibilities for life and intelligence. Understanding our cosmic address transforms astronomy from studying distant objects to exploring our extended cosmic environment and evolutionary history. Discoveries revolutionizing our understanding of the Milky Way are transforming how astronomers study other galaxies. For over a century, distant galaxies served as laboratories for understanding cosmic evolution, assuming they represented processes in our own neighborhood. This approach was limited by the inability to see detailed structure and complex history of distant galaxies. Revelations about the Milky Way's hidden complexity, violent collision history, and ongoing evolution force astronomers to reconsider interpretations of distant galactic observations. Seemingly simple galactic systems may be as complex and dynamic as our own, with hidden stellar populations, ongoing mergers, and intricate structural details invisible at cosmological distances. The VISTA and Gaia discoveries revealed stellar migration, chemical mixing, and structural evolution happen on more dynamic timescales than realized. Galaxies observed at different cosmic distances and epochs may represent snapshots of rapidly changing systems, not stable configurations. Evidence for widespread galactic cannibalism in the Milky Way suggests most galaxies grow primarily through mergers, revising formation models and explaining puzzling properties of distant galaxies. The discovery of extensive dark matter substructure around our galaxy provides templates for understanding similar structures around distant galaxies. Astronomers can use the Milky Way as a detailed test case for dark matter theories, improving predictions about galaxy formation. The 3D mapping techniques pioneered with VISTA and Gaia are being applied to increasingly distant systems. Next-generation telescopes will extend these methods to nearby galaxy clusters, revealing detailed internal structure and evolution of hundreds of galaxies simultaneously. Magnetic field discoveries are driving new investigations of cosmic magnetism. Galactic archaeology techniques are also being extended to distant systems, revealing violent, dynamic evolution may be the norm. The Milky Way provides the detailed understanding needed to interpret observations of galaxies throughout the observable universe. We've only begun to explore the hidden universe around us. Discoveries from VISTA and Gaia represent the first chapter in a new era of galactic exploration, pushing boundaries of cosmic cartography. Future telescopes and space missions will reveal aspects of our galactic neighborhood currently invisible. The European Space Agency's upcoming Euclid mission will map the 3D distribution of dark matter throughout the local group and beyond, creating detailed charts of the invisible structure shaping galactic evolution. These observations will reveal how dark matter streams connect galaxies and trace cosmic web filaments channeling gas in galaxies. The Nancy Grace Roman Space Telescope, launching later this decade, will conduct infrared surveys exceeding vistas, revealing stellar populations throughout the galactic halo in detail, potentially discovering new categories of stellar fossils, preserving information about cosmic epochs. Time domain astronomy, studying how galactic structures change over months, years, and decades, is an exciting frontier. Advanced monitoring systems will track stellar motions, magnetic field evolution, and dark matter substructure in real time, revealing dynamic processes. The combination of artificial intelligence and massive astronomical datasets will uncover patterns and connections. Machine learning algorithms, trained on VISTA and Gaia data, are already discovering new stellar streams, identifying unusual populations, and predicting hidden satellite galaxies. Future gravitational wave detectors will detect mergers of black holes and neutron stars throughout our cosmic neighborhood, providing information about extreme environments and compact objects. Techniques developed for mapping our own galaxy are being scaled up to study the local universe. Within the next decade, astronomers will have 3D maps of stellar populations throughout the local group, revealing detailed structure and evolution of dozens of galaxies with high precision. Discoveries may come from unexpected directions. Every major breakthrough in galactic astronomy has revealed unpredicted phenomena. The hidden universe surrounding us likely contains structures, processes, and connections that will surprise us. We stand at the beginning of an age of cosmic exploration that will enhance our understanding of our place in the universe.